Thank you. So this is work done in collaboration with David Hughes and Chris Jones at the University of Leeds. So many astrophysical objects have observable large-scale magnetic fields which are produced by dynamos. And in these dynamos, the inductive motion of the conductive fluid are mainly driven by convection. Now, these objects are rapidly rotating and they have a low fluid viscosity. So we expect the convective flow to occur at small scale and to be turbulent. So the long-standing question in dynamo theory is, how can you produce the large-scale magnetic field that we're observing with this small-scale turbulent flow? So this is the question that I'm going to address today. And I'm going to discuss a self-consistent dynamo mechanism, which consists of two steps. So first, the formation of large-scale flows, and then subsequently, the formation of large-scale magnetic fields. So we perform a numerical simulation of rotating Rayleigh-Bénard convection. So we have a 3D box, which contains a Boussinesq fluid. It's periodic in the horizontal direction. It rotates with respect to the vertical axis, and we impose a temperature difference between the top and the bottom such that the system is convectively unstable. So I'll first present results from non-magnetic convection. So here we're considering rapid rotation and turbulent convective flows. So the flow here are relatively vigorous. So these two pictures show the structure of the flow. So here what's actually plotted in are the isocontour of the axial vorticity. And so the movie on the right shows so it's an horizontal slice through a computational domain which is taken during the growing phase of the kinetic energy. And we have a multitude of small-scale vortices, so these are the convective flows, and red mean cyclonic vorticity, and blue is anticyclonic vorticity. And you can see that the cyclones start to form a bigger patch. So we have a faster cyclonic rotation vorticity, which is forming here. And on the left, this is a snapshot which is taken during the saturated phase. And you can see that now the flow is dominated by this large-scale cyclone. And next to it, there is actually a weaker anticyclonic circulation. So these large-scale vortices consist of depth-invariant flow, which are mainly horizontal, so they do not transport heat upwards. So in our computational domain, the large-scale vortices grow to the largest permitted horizontal scale. So their horizontal scale is constrained by our domain size. So an interesting question is, if we could make our domain a lot wider, at what scale would these saturate? And this is currently unknown. So a striking feature of this is this cyclone anticyclone asymmetry at large scale. So this is actually quite common in a 3D rotating turbulent system when your axial vorticity is locally of the order of the planetary vorticity. And so what we're expecting for low Rossby number, that is when we increase the rotation rate towards planetary condition, is that this symmetry should be restored, okay? Because this asymmetry is a fine Rossby effect, which breaks the symmetry of the axial vorticity equation. And so this is what was observed by Stefan Stelmach and his co-author. So what they do is they do DNS simulations similarly to what we're doing, but they reach lower Rossby number. And the plot there on the right is a snapshot from the simulation, and you can see that the symmetry is restored. In that case, there is a pair of cyclone and anticyclone of similar amplitude. So now I'm going to move on to the generation of a magnetic field. And what we're really interested in here is at what scale is the magnetic field produced by these flows. So the initial condition is a non-magnetic simulation, and we're going to add a seed magnetic field to it. And decrease the magnetic diffusivity, that is, increase the magnetic Reynolds number up to the point where the flow can sustain a magnetic field. Oops. So this is what the magnetic field looks like at the dynamo threshold for, at the threshold for dynamo action. So here the magnetic Reynolds number is of the order of 300. And on the right, you can see an horizontal slice of one horizontal component of the field. And the magnetic field is concentrated into these bands. And if you compare this picture with the picture on the left, which shows you the structure of the flow, you can see that these bands are located in the shear layer that surrounds the cyclone. And in the core of the cyclone, the magnetic field is relatively weak. So here we have a large-scale magnetic field compared with the scale of the convection, which here would be about 1/10 of the horizontal scale. And right, so this magnetic field is essentially horizontal. There's little vertical field which is produced at large scale. So this large-scale dynamo is oscillating, as you can see here on the time series of the kinetic and the magnetic energies. So their fluctuations are anticorrelated, and these fluctuations are essentially due to oscillation of the large-scale vortex. So the two snapshots at the bottom shows you the axial vorticity during a maximum of the kinetic energy. So here we have a well-developed large-scale cyclone, but during the minimum, you can see that the large-scale cyclone has shrunk in size and it's a lot weaker. So, but it never entirely disappears in this case. So this oscillation of the large-scale vortex are of magnetic origin. They don't occur in absence of magnetic field. And to explain what's happening here, I'm going to draw a little sketch. So initially, we have the convective flow that produces the Reynolds stress that at the origin of this large-scale vortex. And the combination of these two flows produce the large-scale field that we've observed before. Now, the convective flow are going to interact with the large-scale field to produce a small-scale field. And this is detrimental for the large-scale vortex because the small-scale field destroys the coherence of the Reynolds stresses. So, the small-scale field is going to quench the LSV. That's going to lead to the decrease of the kinetic energy, which is followed by the decrease of the magnetic energy at all scales. So when the small-scale field is weak enough, then the large-scale vortex can regenerate and the cycle begin again. And so note here that the small-scale field doesn't need to be very large to destroy the large-scale vortex because in this case the magnetic energy is smaller than kinetic energy at most scales. And an important point here is that this large-scale dynamo only works below the threshold for small-scale dynamo action, because if we had a small-scale dynamo here, the convective flow would continuously produce the small-scale field, which would continuously destroy the large-scale vortex. So if we increase further the magnetic Reynolds number, so here larger to 3,000, then we only have a small-scale dynamo, as you can see here. So on the left, we have a plot of the flow. So again, it's the axial vorticity. And on the right, we have one component of the horizontal magnetic field. So the magnetic field here at the bottom for the large RM dynamo is a small scale. And so it destroys the large-scale vortex, as you can see on the plot of the flow here. So that brings me to my summary. So here we've proposed a dynamo mechanism to produce large-scale magnetic fields. So these are horizontal, essentially horizontal magnetic field, which tends to be concentrated in shear layers. This is an oscillating dynamo, and the oscillation corresponds to cycle of regeneration and suppression of the large-scale vortex. This dynamo works for magnetic Reynolds number below the threshold for small-scale dynamo action. And what's important here is that, so this dynamo relies on the presence of these large-scale vortices, and these form by an upscale energy transfer that is nonlinear in inviscid, so that this mechanism should be robust in the limit of low viscosity and rapid rotation. Okay. And I'll stop here.
Plenty of time for questions. Yes.
So do you mean the period in time or the amplitude? Okay, so the question is concerning the amplitude of the oscillation of the kinetic energy with respect to the magnetic energy. So here actually I was showing a plot of, it was a semi-log plot. So if you compare the relative amplitude, so relative to the mean, honestly I don't even remember what's the answer, but I think for both cases the fluctuations are pretty important, really. Yeah.
Repeat the question.
Yeah. So when I increase the magnetic Reynolds number, then the oscillation, the amplitude decreases. Okay.
Actually, I have a question.
Mathieu?
Maybe you mentioned this, but what's the magnetic Prandtl number that you use for this? And if you were to use a realistic one, how would these results be changed?
Right, so here the magnetic Prandtl number that we're using, so for the, at the onset of the dynamo, it's a PM of 0.2. And so for the case, the large RM dynamo I had, it was 2.5, I think. So what would happen at small PM is a good question, actually, because we don't really know how the threshold of the small-scale dynamo varies with PM. So yeah, that's a good question, but I don't know the answer.
So I have a question. It looks like you have magnetic field wrapping around the vortex. It's like the classic Nigel Weiss solution. Is it?
Well, so here we have, so one thing that maybe I should point out is that these large-scale vortices, because they're horizontal, they can't produce magnetic field by themselves. So we're not sure what's happening. It could be actually, what I think is that the magnetic field is produced in the shear layers because the large-scale vortex acts onto the convective flow so that the MF is coherent there. But so I don't think it's a flux explosion mechanism.
Okay, thank you, Céline.